sure you're as excited as I am to get on with it. In this session, for questions, we'd like to use the microphone here on the stand.
Only the second talk.
Only the second talk, all right. Don't forget what I just said. It's a great honor to introduce Umesh Vazirani. What I really like about Umesh is that he said today that I'm one of his favorite people. And it's very much appealing. And Holographic Complexity is not his title.
Okay, so thanks, John. So, as I was preparing the talk, I realized that a much more appropriate talk would be about the ways in which my path has sort of intertwined with Mickey Benors, and so I switched the title to Computing Undercover with Mickey. So what do I mean by that? So let me just say that when I was a grad student already, I think a couple of years into grad school, there was a paper of Mickey's that I found really interesting, and I worked on it. But it had this feel of, you could call it homomorphic computation, and so I realized that if I look at various things, there are various places where it's not homomorphic computation, but you're sort of computing under the hood, so to speak. Okay, so let me just run through that example because it's such a nice one, and it's in So there was a paper of Mickey's on the cryptographic security of RSA bits, and what it showed, back in the day, it was really hard work to show cryptographic security of bits, and what it showed was, if you're given the RSA function on X, it's hard to compute, say, a bit of X, like the least significant bit of X. Another way of saying it is, suppose I give you a magic box that on input RSA of R, the encryption of R, correctly outputs the least significant bit of R with some probability, meaning on some of the R's it works, on some it doesn't, but more often it works than not. Can you recover RSA of X, or X from RSA of X? Okay. So what was their paper? It said, well, just pick Y at random and compute RSA of Y, and then you perform some binary GCD on X and Y under the cover, under the hood. And now in GCD, you know that you would if you do the GCD properly, you would obtain numbers A and B such that AX plus BY equal to the GCD of X and Y, which you expect to be 1. So now you know everything here, A, B, Y, and 1, and so you can compute X. So very simple outline. Okay, so what you're really trying to do is you operate on the encoded messages to do this GCD algorithm. And this was a very nice, simple algorithm. What you end up doing is this binary GCD is a simple way of computing the GCD of X and Y. You just, if either of the numbers is even, you can you divide by 2. So leave the GCD alone. And if they're both odd, then you can replace X and Y by X plus Y over 2 and X minus Y. And the point is you can perform all these operations under the hood, except maybe testing whether the number is even, but that you can do with the magic box. So this is something that I found really cool back in the day, as a grad student, and I sort of we worked on slightly improving the how well this worked. So the next time I sort of ran into Mickey was in 1993, just before Ethan and I had published our paper on quantum complexity theory. And I remember giving a talk. I think I'd gone to there was a workshop in Israel, and I'd gone to it and given that talk. And the first thing that Mickey and I spoke afterwards, and the thing that he was laser focused on is, so at that time, in our paper we said, well, quantum quantum computers violate the extended Church-Turing thesis. Here's why. And to do that, we had to say, well, quantum computers are a reasonable model of computing, which meant you can efficiently program them, and they are robust to noise. They are digital. So our notion of digital was they are robust to inverse polynomial noise. And the first thing, the thing that Mickey really came and asked me is, well, but don't we want to get this down to a constant? And how can we get it down to, so this was really the uppermost question in his mind. And of course, a few years later, after Peter Shaw came up with his quantum error correcting codes, there was a paper of Aronov and Benor, which you heard about from both John and Dorit. Okay, so the next thing you can say about quantum Hilbert space is it's both large and inscrutable. In what sense is it large? Well, of course, from our point of view as classical observers, if you have an n-qubit system, Hilbert space is exponentially large. Right? But our window into it is extremely narrow. A measurement reveals at most n bits of information. And so we could sort of say, is this all we can do? Nature just prevents us from looking in any further. And so right from the very early days of quantum computing, we understood that there was something important about quantum computation and quantum speedups, which should shed light on the nature of quantum mechanics in some way. And so at that time, the way we formulated this was to say, so we said something like, well, once you have say an exponential speedup, and you can verify it, you can verify that your quantum computer actually solved this problem faster. Well, then you've demonstrated something about this Hilbert space, which would seem to be disallowed by the axioms, in the sense that it seemed like the measurement axiom allowed you only n bits of information at most, and this says no, you can verify that it's exponentially large. And so you could ask the question, well, now that if we think of these as computational probes into the Hilbert space, if you're using computation to look into Hilbert space, what else can we do? And there was a beautiful paper by Aronov, Benor, and Ivan, which sort of said the right, a way you could think about this problem is by thinking about an interactive proof between a verifier and a classical verifier and a quantum computer, where you try to verify not just certain things like factoring, but also, more general quantum computation. And okay, so the model they had was not quite that you have a classical verifier. You have a classical verifier who can prepare, small, constant number of qubit states, and so there's a small quantum channel on which they can communicate quantumly with this quantum computer. Okay, but and the idea still, again, was you end up computing under the hood, right? So what you do is you take your quantum state. The verifier takes these small number of qubits, the quantum states, and encodes them by performing randomly bit flips or phase flips on them, X's and Z's. And this is enough to make sure that the qubit is completely indistinguishable from a random qubit. And of course, the verifier keeps these keys, the Pauli keys, which say how the qubits have been encoded. And now they together carry out this protocol where the computation is being done under the hood. And why can the prover not cheat? Well, because the prover doesn't even know what the qubits look like. The space is sort of hidden. So if the prover sort of doesn't follow protocol, you'd expect that this would be detected. Okay. Now, okay, so I should say that, that it sort of sounds easy, but it turns out to be really hard to prove that this is all correct. Right? So, but somehow, if you want to actually test quantum mechanics in a really robust way, then what you really want to do is you want to answer this question not with an almost classical verifier, but with a truly classical verifier, because then you really have an interactive proof, which means that if it checks out, what you're saying is, well, a quantum polynomial time computer can convince you about what the answer was, but if the answer was no, then nobody, no matter what the computational power can actually mislead you. This would be really quite a strong result. So I said that proving these things is extremely hard. So there's something very there's something really interesting about this setting, because we are standing outside. There's a quantum computer here. It's a black box. It's completely untrusted. We have no idea what it does when we ask it to do something. So we might say, apply a bit flip to qubit number 3, and then do the following other operation, and so on and so on. And then we come back and we say, now apply a phase flip to qubit number 3. How do we know it's even respecting the qubit structure? How do we know? We don't know that it had qubits inside. We don't know how this information was represented. We don't even know that the way the information was represented, it always respects, even if the information was sort of distributed in some non-intuitive way, we don't even know that it respects any qubits. So this turns out to be sort of a key issue that we want to enforce from the outside. So in the protocol of Arnav, Benor, and Iban, what they did was the way they ensured the qubit structure was by encoding the qubits cleverly, so that if the prover did not respect the qubit structure at all, since the prover didn't even realize where the qubits were in the space, if the prover tried to do anything else, it would get detected. Okay, so now the question was, how would we do this if there was just a classical verifier? And so the thing we looked at was, this was with Reichardt and Unger, and we were trying to understand how to simplify these proofs and understand them, and eventually we tried to do this in the two-prover setting, where you have two entangled quantum computers. Right? There are two quantum computers which share entanglement as much as they want, but they can't talk to each other. And as a classical verifier, we interact with these two quantum computers. But both quantum computers are totally untrustworthy, and they might be colluding with each other, without actually talking to each other. So the idea behind, so how would you sort of ask them to do a quantum computation for you and trust it, even though the quantum computers were untrustworthy? So might be untrustworthy. So the answer was that if the verifier plays a CHSH game, one of these tests of entanglement, like a bell test, then what we could show is that what this establishes is that the provers share a Bell state, and they apply, X and Z operators as requested, bit flips and phase flip operators as we request them. So to see this, you have to sort of slightly switch your viewpoint, and you have to say, well, look, a qubit, you think of it as a superposition of 0 and 1. Instead, we should think of it as being defined by two anti-commuting operators, the bit measurement and the phase measurement. Okay, and these two operators anti-commute. But also, if you want to, of course, if you're going to test that these two operators anti-commute, which is what the CHSH game does, then we won't be able to test this anti-commutation property exactly. So we'll only have an approximate anti-commutation between these operators. And so what you can also say is that an approximate qubit is defined by two approximately anti-commuting operators. So what this means is that even though you're sitting outside, there's this untrusted quantum, device, somehow you would imagine that, there's the device should be completely inscrutable, but somehow, these properties of entanglement allow you to actually have more control from the outside than you would imagine, because these boxes are allowed to be, these devices are allowed to be entangled. I'm missing a slide here somehow. But I can talk through that. So now instead, what you could do is also have the verifier play a sequence of CHSH games, n of them, and that's enough to establish if the games are passed with the right probabilities in expectation, then that's enough to show that these devices must share a number of Bell states in tensor product with each other, approximately. And that when you ask to perform an X or a Z operation on these qubits, whatever gate that you want, it's really actually performing those gates. And so once you have that power, you can actually ask the quantum computers to perform an arbitrary computation for you and trust that they actually carried it out. Okay. So all this is in this form of, again, somehow one is operating under the hood, except now the encryption is not explicit, right? So it takes the form of something quantum happening, this kind of entanglement test that tells you that what's happening behind the scenes must look like this. So it's not really quite homomorphic encryption, it's something else. But it's still, operating undercover in some form. Now, these ideas sort of got amplified even further. So these tests for that you had a lot of qubits, entangled qubits, Bell states being shared. These so Natarajan and Vidic had these beautiful tests which played these these sorts of CHSH games, but in this setting of linearity tests and low degree tests, and showed that you could make these much more efficient. And then in parallel with this, there were other things you could do quantumly. Again, sitting outside, as somebody classical, you could look into, if you had a untrusted quantum device, you could use it to generate truly random numbers, statistically random numbers, in a way that you could actually check classically. And so these were the kinds of ideas that played a role in this in the MIP star equal to RE result. Okay, so there's one other setting in which you can study this problem again. We'd like to come back to one quantum computer and and a fully classical verifier. And can you actually, in this setting, could you actually verify that this quantum computer was doing what it claimed to be doing? And so we don't know how to do that, but there's you can add one more wrinkle to it, which is you can say, let's assume that this quantum computer is running in polynomial time. So now, if it's running in polynomial time, this opens the door to post-quantum cryptography. So, in other words, we can assume that there's a crypto system which is classical. So you can encryption and decryption is classical. You can decrypt if you have a secret key. But if you don't have a secret key, even a quantum computer cannot decrypt. So now this gives some sort of, it sort of levels the playing field somewhat in the sense that the quantum computer is more powerful. The classical computer has a secret key. And in these settings, what Urmila showed is that you can carry out two different kinds of protocols. You can do fully homomorphic encryption, meaning you can, if you want to compute some function under an encryption, but now you want to compute with you want to carry out a quantum computation, then you can do that with a classical verifier. And the other thing she showed is that if you want to verify that this quantum computer really carried out a computation and gave a result, and that result, if it was not in NP, you don't know how to verify it. How do you know that it's even the correct answer? Well, you could do that again in the same setting. And the idea again, the building block again that makes this possible is a very simple protocol which allows you to do this. It allows you to, it allows the quantum computer to set up a random qubit. It's either 0 plus, it's either the plus state or the minus state. And since it's 50-50, that's like a random bit. The quantum computer cannot distinguish what the bit is. But on the other hand, the classical verifier ends up with an encryption of this bit B. So given the secret key, the classical verifier now knows what this qubit is, but the quantum computer doesn't know what the qubit is. On the other hand, the quantum computer can manipulate this qubit, and so now you have this more symmetric situation. Okay, so the reason I spoke about all this was to say that in some way, yeah.
So the verifier here runs the same amount of time as the quantum computer, right?
Yes.
Because he's checking at every stage that the operation was done properly.
Yeah. So both the verifier and the quantum computer are polynomial time.
No, I understand, but but he's not working less. He's working at the runtime of the verifier.
Yeah, would be
the same as
yeah.
the computation.
Yeah.
So encrypting the thing, the guys on the other side is doing the quantum computation steps under encryption.
Yeah.
And you sort of check it, but not just at the end. You check also throughout.
Well, you could, in the protocol actually the quantum computer actually computes a witness, a ground state of a local Hamiltonian, and then the verifier checks offline.
All I'm saying is how much interaction is between them? I guess that's the way I should phrase it.
Ah, I see. Yeah, so...
Is it the number of steps of the computation, or is it just at the end? It's the number of steps.
It could be parallelized. Is that what you're asking?
No, what I'm asking is...
The amount of interaction is going to be polynomial in them.
Eventually, they will be able to check it faster than the time that you the computer, in the way that you do classically with delegation.
Yeah.
The time to check is much faster than the time it took you to compute.
That's
That's not the case here.
No,
No, but the verifier can't do the computation because it doesn't have a quantum computer.
no, but what Shafi is asking is, would you have a, can you does this protocol allow you, if the quantum computer is running for time t,
Yeah.
and then the classical verifier should run for time polylog t or something?
Just read the-
Yeah.
I mean, in principle, yes. but
Yeah.
The same question I was asking you.
Yeah.
So what's the conclusion?
No.
No, we don't know.
We haven't tried this, we don't know how to do it.
Possibly we'll check.
It's possible, but we don't know. Okay. So now, I want to turn to something a little more speculative but where, where this, what's happening, under the hood is happening because of physics rather than computation. So there's this big question in physics, which is reconciling gravity and quantum mechanics, general relativity and quantum mechanics. And so over the more than the last quarter century, there's this approach that's been taken, which was formulated, I think, by Juan Maldacena, which is called this ADS-CFT correspondence. So what it posits is, that there's a duality between a quantum theory of gravity in what's called the bulk, a d-dimensional space, and a conformal field theory or quantum mechanics on the boundary, a d-1 dimensional space. So that's, it's called this holographic duality. John mentioned it, in terms of the holographic principles. And what does it mean there's a duality? It means that there's a mapping between these two spaces, so that states get mapped to states and operators to operators. So whatever is happening in the bulk, you map back and forth. And in fact, there seem to be different views about the nature of this duality, whether it's just a mathematical duality or whether there's a physical reality to it. But certainly I think there are physicists who would talk about, and I think Susskind talks about this, Lenny Susskind talks about this as that these are two views of the same reality. So, this notion that we are trying to reconcile gravity and quantum mechanics, instead the answer is, no, you don't have to reconcile them. They are the same thing. They are the same thing viewed from two different viewpoints in some sense. Okay, so about 10 years ago, Lenny Susskind, he observed the following paradox. So the paradox is this, that there's a certain kind of basic solution, solution of Einstein's equations for which he could show that, on the one hand, the volume of the black hole, it's a certain kind of black hole, grows for an exponential amount of time in n. So n is the entropy of the black hole. So it's some measure of complexity for the black hole. On the other hand, what's believed is that the Hamiltonians on the CFT side, they are scrambling, which means that the amount of time it takes for the quantum state to thermalize is roughly linear in n log n, n polylog n. And so you would expect that almost any of the normal things one would go to measure about that quantum state should have thermalized, and so it should be constant. So he asked, well, what quantity, but because of the duality, the volume must correspond to something in the CFT. And what could this quantity be that keeps growing for an exponential amount of time? And the answer he came up with was, obviously, it is the quantum circuit complexity of the CFT state. So as the CFT state is evolving in time, you can talk about the quantum circuit complexity, meaning you say, well, let's start with the all zero state or some simple state, and now let's find the size of the minimum quantum circuit that will output this state, the state at time t, and so that's the quantum circuit complexity of that state. And his answer was, this must be dual to the volume. Now, I happened to hear this talk in 2014, and my reaction was, surely, circuit complexity, it doesn't have the right properties, right? You can't feel circuit complexity. So any physical quantity you should be able to measure, which means you can feel it directly, right? And so this obviously is not the right answer, and it'll all get sorted out, so I won't worry about it. But a few years later, this was still going strong. So, oh, sorry, that's Lenny Susskind. So a few years later, this was still going strong. So we started thinking, well, surely there should be a way of showing this, and surely the answer should have to do with, the reason we think complexity cannot be felt is because of pseudo-randomness, and there was this paper, by Ji Liu and Song, beautiful paper showing that you can efficiently create pseudo-random states. So you can create states on n qubits by using some sort of a pseudo-random function. So you base it on any one-way function, and you can create the state on n qubits so that even if I give you polynomially many copies of this state, you can't tell whether I gave you this state or a completely random state, a Haar random state. Now, the unfortunate thing about this was that so there are only restricted operations allowed in the CFD. There are restricted kind of states you can create there, so you cannot use this construction there. And so with Adam Bouland and Bill Pfefferman, we showed that, in fact, in this setting that Lenny had, the CFD state would be pseudorandom. We argued that it would be pseudorandom. So we concluded either Lenny must be wrong, his conjecture must be false, or this dictionary map must be exponentially hard to compute, or for a technical reason, the quantum extended Church-Turing thesis must be false in the bulk. And then after some time, we examined our argument more carefully, and we realized that far from showing that his conjecture was false, what we had ended up showing to our satisfaction was, in fact, he must be right in some form or the other. And so why was that? Well, because once you have, once you create these, you say, well, as you're progressing your pseudo, your state in the CFD is pseudo-random, well, then it follows that whatever is dual to volume could not be some easy to compute function, right? Because trying to tell the difference between the state at time n squared versus n cubed, each of them is indistinguishable from random, so they are indistinguishable from each other. And so unless you take exponential time, you can't tell the difference. So now, whatever it was that's dual to volume can't be that simple to compute function. Right. So whatever is dual to volume must be a very hard to compute function. At that point, what's the difference? We may as well assume it was a quantum circuit complexity, right? So for us, the quantum circuit complexity was sort of it was standing in for something. It was a proxy for something. It's a perfectly fine proxy, and you could look at the actual physical characteristics and say exactly which proxy do you want, but at least for us, this sort of settled the matter, and so it said, well, from our point of view, the conjecture is fine. So now this left us with one of these two options: either the dictionary is exponentially hard to compute, or the quantum extended Church-Turing thesis is false in the bulk. And of course, you could say, well, if the quantum extended Church-Turing thesis is false in the bulk, then certainly the dictionary should be exponentially hard to compute, because you're going from something easy to hard. So you're down to just this middle possibility.
If the dictionary is hard to compute, it can be that the state is not complicated, at least in the boundaries in its CFT. So why do you want to say that implies a complexity? Because it's not complex in CFT.
No, what I'm saying is that whatever the observable is that corresponds to volume, it's got to reflect the length of time that the state had been evolving, right? But we're saying the state is pseudo-random, so whatever your observable is, it's going to be able to distinguish for me that the state evolved for time n or n squared or n cubed, right? Whatever it is, it's going to take you exponential time to compute it. At that point, we may as well let it be,
But if all that computing is done in order to trigger the dictionary, then you still consider...
No. So this is not in the dictionary. This is you're just sitting on the CFT. You're saying what's your observable.
You're going to have to understand well.
Yeah. Okay. So let me just. Okay. So there's another side of this, which is there's another aspect to this quantum gravity, which is this belief that in fact geometry equal to entanglement in some sense. So in what sense is it equal? It comes from this Ryo-Takanagi formula, which says, if you have your bulk state and your boundary state, and now you partition the boundary state into two parts. Let's say this spherical cap on the boundary, and now you've taken your quantum state on the boundary, you partition it into these two parts. So now there's some entanglement entropy between these two parts. Well, what the Ryo-Takanagi formula says is that in the bulk, if you look at the area of the minimum surface bounding this cap, it must be equal to the entanglement entropy of that patch on the surface. So in this sense, entanglement seems very tied into the geometry of the. And of course, this formula imposes conditions on the entanglement entropy of CFT states. They can't be arbitrary states. They must have a geometry associated. Okay, so now just like pseudo-random states, you can now create pseudo-entangled states. So you could create states, quantum states, which have very different entanglement from each other across some or all cuts. But you can't distinguish this pair of states in polynomial time, even given polynomially many copies of the states. But again, like with pseudo-random states, the entanglement entropies do not directly satisfy the RT formula, so we can't use these states to say, look, there's something extremely hard, there's something very hard on the boundary telling what the entanglement is, which corresponds to geometry in the interior. But in fact, with Li Jie Chen, what we showed is that you can create two distinct geometries or pairs of distinct geometries so that you can efficiently sample a pseudo-entangled state corresponding to either geometry A or B. And now if you could, so these are pseudo-entangled, so telling them apart is exponentially hard. But on the other hand, the geometry can tell them apart. So what we do is we work in a tensor network toy model, which has been used before in this area. The geometry is the structure of the tensor network, and the CFT state is a state described by this tensor network on the boundary legs. All right, so now where does this leave us? Well, with a lot of questions. So the first question is, well, it works in the toy model, but those toy models were used for in certain contexts. In this context, are these toy models even valid? Are they? Is a toy model missing important elements of this ADS-CFT? So could you actually construct such states? If it does, then maybe this shows that the dictionary map remains computationally hard even in the absence of black holes. So it would sort of say, well, it's just because of geometry. It's not black holes that are causing this exponential complexity. The other thing you could say is, are there, maybe there are fundamental reasons why we couldn't possibly access both bulk and boundary observables. So everything is protected, but maybe we want to sort of say this way, extract this principle out and formulate it carefully to say, this kind of information cannot be accessed on both sides. Or if it can be accessed on both sides, well, then that would say that maybe the quantum extended Church-Turing thesis is false, because then you would be able to distinguish pseudo-entangled states and break a one-way function by accessing geometry. What would that mean?
Silvio can come and hook up. We're running a little late, but while that's happening.
He's not here, he's remote.
Oh, sorry. Well, then he doesn't have to do that.
Yeah.
Okay. That explains the microphone.
Silvio,
For-
can you hear us?
Hold on a second.
Okay.
Are we done?
Go, while we're